Hi, and welcome to the second part of the video where we're going to continue with the work that we did in the first part, where we implemented the logic of the game of life by John Conway, which is a cellular automata logic to propagate cells on a 2D grid. But on this exercise, on this second part, what we're going to do is we're going to modify what we did in the previous one, where we just worked with a flat list of data. And we're going to do some changes and some tweaks so that we can work with the full data tree structure, which integrates better with the ecosystem of Grasshopper and how a lot of these Grasshopper components work. And also, thankfully, we will learn a little bit of how data tree structures work. Okay, if you stick around, we will end up this tutorial by applying the cellular automata logic, not just to a stupid 2D grid of points, but to an actual surface that has been subdivided in cells, so that we can propagate these elements on top of that surface. All right, how cool is this, huh? So stick around if you want, and let me show you how we can do this. Let's get to it. So the first thing that I'm going to do is I'm going to rewrite a little bit of the definition that we had from the previous video, so that I remove all the flattening and all the data simplification, and I just stick to my two-dimensional grid of rectangles with a data tree structure. And then I'm going to reshape a little bit of the C# component to take that data, to take that new data forms. So I'm just going to go in, I'm going to remove all of this here. I'm going to remove the points. So I'm going to keep the rectangle, finding the centers, point containment, etc. And I'm going to remove all of this as well. So that now I have my list of rectangles that has a tree structure, and I have my list of whether if the center of those rectangles are inside the curve, this curve here, or not. Just to verify that I have a tree structure, I'm going to use the tree parameter viewer here, and I'm going to plug it to the rectangle box. You can see that I have a data with 50 branches and 40 elements in each branch, and that the equality test has the exact same data tree structure. If you double click on this component, it gives you this nice tree-like sort of visualization, which is kind of cool. I don't know how useful it is, but it's cool. So, all right, so I think we're good to go. And then what I'm going to do is, in the C# script component, I'm going to remove the ticker. We don't need this anymore because we're going to keep using the timer technique. The cells are going to be the true and false pattern that we want to iterate over. And then for rows and columns, we're going to remove that because we're going to read that information directly from the data tree. Okay, so this is, and then this is very important, the cells, this is not a list access anymore, this is a data tree access. So I need to change this to tree access. This is not going to be working anymore, obviously. And then now I can go in and deactivate false and start working inside of the component to translate the data tree into the float array that we need, and then keep going with that. Okay, so let's get that going. I just opened my C# scripting component, and I can see already that the input cells has been changed to data tree. Okay, which is great. So what are we going to do? Well, if you remember from the previous video, we had some sanity checks here to see if things were going well. Now we may have to change this a little bit because now I don't have the number of rows and the number of columns. This is something that I will need to take from the data tree. So I think that the first thing that I would like to do is, before I do any sort of checks here, I'm just going to comment this out for the time being. And then what I would like to do, actually, I'm going to comment everything out, because, and then I will start turning it on and off as soon as I start rewriting things, because otherwise I'm not going to be able to run the component. It's going to give me a lot of errors. So yeah, so I'm going to turn everything off, and then and then start rebuilding all the code little by little. So the first thing I would like to do is I need to write something that translates from a data tree of cells into a two-dimensional array. Okay, so that should not be very hard. So what I would like to do is I'm going to go all the way down, and I'm going to write myself a function here to perform that that functionality, so that the code is not so messy. Actually, I'm going to take that back. I'm just going to do that here, and maybe by the end of the video we can just move things from one place to the other and just turn them into functions. Okay, so what I'm going to do here is I'm going to say convert data tree to the array. All right, sounds good. So what first thing that we need to do is we need to figure out what are the names of rows and columns from the data tree. So I'm going to initialize two variables, rows and columns. I believe this is the name that we used before. And I'm going to look at the data tree, and I'm going to try to figure out this information. The first thing that I would like to do is I would like to remember that rows for me were how many elements were contained in each one of the branches, and columns were how many branches the data tree had. So that should be very easy. So the first thing I'm going to do is I'm going to look at the data tree and see how many branches it has, and that's going to be the number of columns. So what I'm going to do is I'm going to say columns is going to be equal to cells, which is the data tree, and if I add the dot notation, you can see that I have a lot of properties of these elements. So for example, of the data tree, I can ask how many elements it has. So for example, for this data tree, I believe it was 2000. I can ask how many branches it has, how many paths. Here in branches, I can actually get a list of those branches, all right? And then there's a lot of other things. You can merge them together. You can get the paths. The paths are those like numbers on the top left corner. So this thing here, this is the path. So for this one, what I would like to do is I'm going to take branch count. Branch count is going to be the number of columns. And I'm going to, here I'm going to print columns is going to be equal to columns, and then I'm going to execute this component, which tells me 50, so that's great. And then for rows, what I'm going to do is I'm going to assume that this data is correct, and that this data tree is correct, and whoever generated it in a good way. And I'm just going to look at the first branch. I'm going to look at how many elements are in that branch, and then I'm going to assume that all branches are the same. This is an assumption. You should not rely on assumptions. You should write code to check things. So we should actually write a for loop to go over all the branches, make sure that they all have the same elements. Yeah, why don't we just do that? Let's just do that, just in case. So this would be like sanity, all right? And then what we can do is I can say I'm going to get a list of I'm going to get my branches, which is going to be cells.branches. So this is going to be the list of branches. And what I have here is a list with all these branches one after the other, so that I can now access them. So I can go and say, for example, for each branch in branches, or actually this is a little redundant. I can probably just do cells.branches, all right? For each one of these, what I'm going to do is I'm going to say, I'm going to first look at the first branch. So cells branches 0, all right? And I'm going to get how many elements it has. So count. This is number of elements in the first branch. Okay, and then I'm going to go over all of them, and I'm going to check if they're all the same. And if they're not, I'm going to give the user an error. So if branch dot count is different than rows, then create an error component dot add runtime, and you've seen this one, runtime message level dot error, not a square grid, for example, and stop executing stuff. Okay, and then here I'm going to now say rows is equal to rows. I'm going to run this code, and I see that, yep, I have 50 columns, so 50 branches, and 40 elements per branch. Okay, so that's good. And perform some sanity. Let's actually, I'm going to write here, figure out number of rows and columns. And now here I'm going to say convert DataTree to the array. Cool. So what am I going to do? I'm going to say I'm going to create a Boolean array with 2 dimensions, like we saw in the previous video, which is going to be input cells, and that's going to be a new empty array with 2 dimensions. And remember that we said the columns was going to be the first dimension and rows was going to be the second one, right? And then now what I'm going to do is for each one of these branches, I'm going to iterate over each branch. I'm going to take that branch and I'm going to take each element of that branch and I'm going to start adding it to the 2-dimensional array. So for each element of cells.branches, so for each branch, here, what I'm going to do is I'm going to write a for loop to go over each one of those elements. So for int I equals 0, I is less than, actually I'm going to use a different technique. Here I'm going to say for int j equals 0, j is less than cells.branches branch count, yes, and then j++. So those are going to be the columns, and then here is going to be for int I equals 0, I is less than, I'm just going to take here bar, the branch is going to be cells.branches j. And then here is going to be branch.count. So how many elements are in this branch? And with this for loop, now I have 2 variables, I and j, which I can use to point to a particular object in the data tree. So here, the Boolean would be, value would be, for this branch that I'm currently in, element number in position number I, right? And now that I have I and j, I can say on input cells, on position j for columns and position I for rows, just save this value that I just fetched from the data tree. Okay, is that right? It looks like nothing is complaining. So I have my input cells as a data tree, as a 2-dimensional array, which I could probably now plug into the code that I used to have here. So for example, let's say I don't need this anymore because this check is already implicit here on this one. I'm going to turn this in. So initialize calculations. So if reset equals true, then previous cells is going to be a new array. Okay, previous cells is going to be a new array, where before I was copying directly from the list of the cells here, when this was a one single list. Now what I need to change is, because now I have a double array, I can actually just remove all of this and say that previous cells has to be equal to my input cells. I think this should work. All right, so this is going to work so far. Yep. And now a new array of live, dead columns, blah, 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 new cells. I think this looks right to me, etc., etc. We're probably going to hit some problems, but let's try to run this. Object reference set to, okay, so what is this? Previous cells. Okay, this is because I have not reset this yet. So if I reset and I start, what is the curling pattern? These are the rectangles here. Okay. So what we can see is that the component is working. And then as I do false, my previous iteration is here, my new iteration is here, and then if I scroll down enough, I can probably hit some elements that are true or false. Where did we find a good chunk of these ones before? Here. So you can see here, you see this one was true, this one was true, and this one remains true, whereas this one became false. So that is great. It looks like I think the connection is laggy, huh? So I think this is good. The only problem is that right now we still have all the elements in one long list, just because we have not taken care to switch the output, and then from a two-dimensional array, which is what we had, switch it to a data tree. So let's do that here. Now switch back from 2D array to data tree. Okay. So what we need to do is we need to take new cells, which is the let me say it. We need to take new cells, which is the array that contains the elements, the pattern, and we need to create a new data tree with each one of the rows, which each one of the rows in the two-dimensional data tree is a list on the data tree, and we have as many data trees as columns in our data tree. So let's do that. The first thing we're going to do is we're going to create an empty data tree of Boolean objects. That is as simple as saying data tree Boolean, and I'm going to call this, for example, new cells tree. Okay, which is going to be equal to a new object of the type data tree that I'm going to initialize as empty. Okay, great. The next thing that I will do is I want to remember that I want to output from my component a data tree that has the exact same structure of the original data tree. So I need to remember that I have as many columns as branches, and inside of these branches I have as many elements as rows. So I'm going to create, like as we have done before, I'm going to create a for loop to iterate over all the columns, the amount of columns that we have. So that's going to be here. And for each column, what I'm going to do is I'm going to read from the original data tree, the one that came into the input. I'm going to read what the path of each one of those branches is. So the path is this address here, which is in Grasshopper is a GH path object. So what I can do is I can say from the cells data tree, which is the original that you gave me, let's take a look at the list of paths. So you can see that this is an interface for lists. So from the list of paths, give me the one at position J, and you can see how the return is this element of the type Grasshopper path. Okay. After we do that, now we have a we know which is the path that we want to add each element to, and then I can just create a new for loop where I'm going to iterate over all the rows. And then now that I'm in my second for loop, I know where I am on the J position of the data tree, that is columns or branches. And with I know where I am in each one of the rows of my two-dimensional array, or each one of the elements in the list within the branch. Okay. So what I can do is, now that I'm here, I'm going to say, I'm going to first take the true or false value that I have calculated in the two-dimensional array new cells. So new cells, J first, I second. So this is whether if the cell is alive or is dead. This is the calculation that I just did, right? And what I want to do is I want to take that value, I want to add it to the data tree, but I want to add it in the path, in the right path that I just calculated. So that is just as simple as saying new cells tree dot add. And if you can see, as I click add and I open parentheses, I have two overloads. Just add the data in the first branch that you have, or add the data with, I'm going to do this again, add the data on the Grasshopper path that I'm giving you as a reference. So very simple, I can just say value, and then here I can just add it to the path that I took from the original data tree. Great. If I do that, I should be able to run this code, and I want you to notice that here on the output B, I did output this new cells tree that I just created. Okay, and which is great because you can see that here on new iteration, we have the data tree with the 2000 elements, but here on B, we have the same data, but instead is with the original path, and it has all the branches one after the other, you know, which matches exactly, I'm going to just to prove you, which matches exactly the data structure that was present on the rectangles that we created for the grid. So they both match identically, which is great because now everything that needs to read from these rectangles is going to have a very easy time to do that. So now we can plug in our B output to the call pattern, and because both trees have 2000 elements in 50 branches, you see they have both the exact same structure, then this component can work perfectly and take both inputs and match them and remove. So now I can say connect the timer, let this go, and boom, my component now works with data at the tree level. Obviously, we could have done this from scratch from the beginning, but it's a little more tedious and perhaps a little too abstract, so I wanted to do it this way to like build up in complexity with these different data structures, okay? So I think what we're going to do now is I'm going to fix a little bug that so when you start, it doesn't start with, when you reset, it doesn't reset to the original ones, but to the first iteration. So I'm going to fix that. And then we're going to have a little bit of fun. So we're going to apply this logic, but instead of like a flat, boring two-dimensional grid, we're going to apply it to a surface in three-dimensional space. Okay? Let's get to it. The first thing I'm going to do is I'm going to open the C# component, and I'm going to create a new variable that I'm going to use to keep track if the user just went from pressing reset through to turning it to be false. So I'm going to write this component, this variable, and it's going to be called something like did just reset or something like that, which I'm going to initialize to false, for example. Now I'm going to use that variable all the way up here to make a decision about what to output. Okay, so I'm going to go here and I'm going to say if I'm going to figure out if I need to perform calculations or not. Okay, which I'm going to do by creating another variable. For example, that I'm going to say perform iteration, which I'm going to initialize it as to true. Okay, so let's see if this component should be performing its calculation, because what I want is if the user is on reset or if the user just reset on the previous iteration, then I don't want to calculate anything. So let's do that. If reset equals true, or if reset, then at this time I should not perform any iteration, right? So I'm going to say perform iteration equals false. Okay, now, but I also want to keep track, I also want to keep this in memory, that the user just reset the simulation. So just did just reset equals true. Okay, and now somewhere down here I'm going to say if no calculation, then exit with original data, with input data. So here what I'm going to say, if perform iteration is equals false, or if this is the case, then here I'm just going to take the data that is coming in cells. I'm just going to output it right away. So that's probably going to be, I'm just going to say, yep, I'm just going to do that right away. So I'm just going to say new iteration, the data that I want to output is going to be equal to cells, and then just return, just don't do anything else. Don't continue executing this component, all right? Let's see if that works. So it doesn't. Let me restart this. So this is true now. What I'm doing is, because it's true, I'm piping this data out through my component, and because this is false, now the object is not set to an instance of another. So there's something that I need to change. But right now, this is working well. When this is true, the data is just going through my component without any changes. Okay. Something that I forgot to do before is whenever we don't perform a calculation, so whenever we don't move the iteration one instance, something that we need to do is we need to make sure that we initialize this data here, previous cells, and that the data that is coming, we turn it into a two-dimensional array and we leave it here saved for next iteration. So this is what I'm going to do now. So what I'm going to do is I'm going to go here and I'm going to take the previous data, and I'm going to say previous cells is going to be equal to a new Boolean array of dimensions column and dimensions rows. All right. And now I'm going to copy something similar to what I did here, which is converting the array. So store data for next iteration. And I'm going to copy this here. I'm going to take all the elements from the DataTree cells. I'm going to retrieve every branch. Then for each element of the branch list, I'm going to take that value and I'm going to save it into previous cells. Okay? And then I finish that by outputting this component, um, output input data with no changes. So that's going to be this, and I think we should be ready to go. Let's see if this works. So now I'm going to turn this on, I'm going to turn this off, and I have an error here. The name column doesn't exist, it's columns in plural. Okay, so we turn this on, we turn this off, we turn this on, we turn this off. Okay, that looks great to me. And finally, what I would like to do is I would like to avoid the fact that when I turn reset off, it just triggers one execution. So that's why I added this variable before. So what I want to do is I want to say, let me here, if reset is true, then you should not perform the iteration, and you keep this Boolean variable that I just reset, you make it true so that we know that this just happened. But if reset is not true, if it is false, but else if, but it turns out that did just reset equals true because we're coming from a state where we did set up that on the previous update, then make that one false, but still do not perform any iteration. Okay, let's see if that works. I'm going to hit OK. So this is true, and then as I turn this to false, this doesn't go anywhere. True, false, true, false. But then as I plug this in, then it starts simulating. Let's see if it works again. True, false. True, false. And then I can see this happening. Okay, so our component can now spit out, can take an input of data trees, and it can output a data tree with the same structure, and then it works a little bit better with this tiny debugging that we have done to the reset function. Okay, so awesome. So I mean, this was a lot to take. This was very tedious. But how about we take some time to like have a little bit of fun, and then apply this technique to not this boring grid of 1x1 rectangles, but we apply this onto a surface. Great. So let's do now. So let's do that. Let's create a surface. Let's subdivide that surface into a bunch of isotrims. Then let's figure out some way of deciding which ones are going to be the starting points in this situation, and then we feed that to what we already have, and we should be good. So let me go back here and create a nice surface. How am I going to do that? I'm going to go ahead here and create like a napkin kind of surface, curve, sort of this kind of thing. I'm going to move this here, more or less. Nope, I'm going to move that here. All right. And then in the front, I'm going to say, I want to create another set of curves from here to here, here, and here. Sorry, and this point here, exactly. And I'm going to create another one from this point here. And as you guys can see, I'm terrible at playing Rhino. All right, but this should be good enough. So surface, how can I create a surface from boundaries? Is that, there was such a thing, right? There was such a thing, a surface. From edge curves. There you go. There you go. And then you can see that. Okay. So that's my surface. Great. And I'm going to bring this in as a, I'm going to bring this surface in as a B-rep, for example. I'm going to bring this as a B-rep or as a surface, maybe, I forget. And then I'm going to take this and I'm going to say subdivide by isotrims. Okay, so domain of the subset. Base surface is going to be this one. And I'm going to say, well, here I'm going to create a domain. And I'm going to take a domain. Let's first extract the domain of this surface here. Divide the domain of this surface into 10 elements and 10 elements. I'm going to crank this up here a little bit. So I'm going to say 50 and 60 and 50 as well. So let's make this square. And these are going to be the subdomains. So these are going to be, you guys can see all the subdivisions that we made here. These are going to be the subdivided surfaces. I'm going to hide this from the view. I'm going to hide the surface from the view. So these are going to be our new cells of sorts. For each one of them, we're going to find the center. So those are going to be here. And now I'm going to create, for example, a sphere here at the center. Or a box. I'm going to create a sphere that is a little, yes, I'm going to create a sphere like this big, which is going to cut through the surface. I'm going to bring this sphere here. I'm going to hide it from the plane view. I'm going to hide it from here. And then brep containment is a point inside of a brep. So are these points here, are these points here inside of this brep, and then what I get is a list of trues and falses. Okay, and turns out this component is a list, is not a data tree. Yeah, the problem I had was that I thought, this was my bad, I thought the subdivide component gave us as an output, it gave us a tree with the domains and the subdivisions, and therefore we could use the component, but it turns out that it doesn't. So we could use the file that we created in the previous video, which takes a flat list of elements. But since we're here, why not do it a bit more cleaner, a bit better, and give some structure to this data? So somebody in the chat just suggested me to use PartitionList, which I wasn't aware of, but it's a really good component. So with this component, you can take a list and subdivide it into chunks and create a data tree structure out of it. So I can take that and I can say I want 25 trees, and therefore now I have this data structure that has 25 branches with 25 elements inside of it. If I plug this in, now all my data downstream has the data tree structure, and therefore I can plug this in here. So I'm going to save this as a new file, and then I'm just going to first of all, I'm going to plug in here the cells. Sorry, I'm going to plug in here the true-false pattern that I want to follow. I'm going to reset this, and then I'm going to plug in here. I'm going to plug what I want to call out of this. So this is going to. I'm going to hide this. I'm going to hide this. I'm going to hide all this stuff as well. Okay. And this curve, I'm going to hide it too. So I have my surfaces, I have my list, and then here I have no elements. And why is this not rendering? Untrimmed surface. Oh, because like I don't need to do a planar surface out of them. I just need to show these guys. Okay, so are you ready for this? Is it happening? Are we doing a, let me crank the numbers up a little bit. So 50 here, and 50 here. Okay, and let me reset the component. And now we have our starting 50 cells. And as I press go, this is going to not iterate. And then as I turn this in, boo, three-dimensional game of life. Yoo-hoo! With all the tiny chunks of that original surface, which I could turn on just for the sake of visualization. Yes. So how cool is that? Huh? Let me do this again. I'm going to turn this off. And the 1, 2, boom. And then we have this propagating pattern that flies and that propagates over the surface and that it wraps around it from one side to the other. Yoo-hoo! Wonderful. It's taken us some time, but I think we did something pretty cool. Now we have a tool that, given any data tree structure of elements, true and false elements on a grid, it can perform a game of life like cellular automata simulation on it. And we can use to fetch or to visualize or to clean or to parse whatever, any kind of two-dimensional grid in space. We started off with a 2D grid of points. We were able to apply this logic to a surface that we subdivided in iso surfaces, okay? But as you can imagine, the possibilities here are endless. So there are a lot of things that we can do. So for example, we can now change the rules of how the game of life works. And I believe, for example, rule 3 and 6 is also a very popular one because it generates a lot of repeating elements, I believe. You can apply this to any kind of geometry that is 2D, that it can be formed in a 2D grid. So for example, a 2D grid of circles, a 2D grid of I don't know, whatever. It doesn't really matter the structure. But you can also think about applying this logic as well to to elements that are not a two-dimensional grid. So for example, you could apply the same, not to this component, you would have to rewrite a little bit of it, but you could apply this to a grid of triangles. You could apply this to a grid of hexagons. You could apply this to a three-dimensional grid of cubes, for example, like a voxel field. And what's interesting, just because the notion of elements that are connected between each other and performing calculations to find how many neighbors each element has, and then making decisions about whether if that element stays or not based on how many elements, how many neighbors it has, can be applied to any kind of structure of elements where you know the neighboring connectivity between them. We've done it very simply for things that had 8 neighbors around in a 2D grid, but anything that you can establish relationships with, a grid of hexagons, a grid of triangles, even a Voronoi pattern, because you can use the Delaunay triangulation to define which elements are neighbor to each ones. That is something that you can very easily do. So I'm gonna leave that up to you, to the viewers. If you wanna take this code and like rewrite it to apply this cellular automata simulation to some other kind of geometry, whatever, that's totally up to you. But if you do something cool with this, make sure to share it with the community and like to send me a text, send me an email, Instagram, Twitter, and I'll be happy to share it with the community as well. We could add colors to this based on some rule. There's tons of things that can be done. Okay. So with that, I think I'm gonna leave it here. That was a lot, but I hope you guys learned, and I hope this was fun. Thank you very much, and if you do something cool, make sure to let me know, and make sure to subscribe to the channel to get notifications about new videos, new posts, new tutorials, and new live streams. Okay? Thanks a lot.